Hello, everyone. This is the final presentation for the LambdaBuffers project for the Catalyst Fund 9 milestone. The LambdaBuffers started a year and a half ago with the Catalyst Fund 9, and I'm happy to say that it was the support for LambdaBuffers was extended through Catalyst Fund 10, where we are planning on adding additional support for languages, concretely Rust, JavaScript, and Icon. Um, I will just run through what the Lambda Buffers toolkit is and which problem it tackles and how it solves it. And finally, I will take you through the Lambda Buffers Cardano demo, which is one of the outputs necessary to close off the final milestone, and where we will show how concisely we can lay out a typical Cardano DApp project and how uh, much less code we have to manually write because of Lambda buffers. So Lambda buffers is a toolkit for sharing types and their semantics between languages. Let's unpack this a little bit more. So in traditional software engineering, programs are written in different languages, but at the end of the day, they have to communicate between themselves, communicate with certain messages encoded in certain format, like JSON, CBOR, XML, whatever. Writing how things are encoded and decoded is very tedious to maintain, to test for correctness, and it's just unnecessary and error prone. This has been automated away very effectively by the existing tools in this space, such as protocol buffers. Lambda buffers is essentially achieving the same thing uh, by introducing a couple of novel ideas and mechanisms. Uh, One thing that Lambda buffers tries to do is share type definitions between different languages, but also share semantics. What is semantics? So, given a certain type, a notion of equality can be defined for it. When in Lambda buffers, we specify a certain type and we say that this type supports equality, the same equality notion will be implemented in all of the supported Lambda buffers target environments, whether that is Haskell, PureScript, Rust, or whatever what comes next. We also support this notion of semantics through something called type classes that languages like Haskell already has, and PureScript as well. They are literally called type classes in those languages. And in Rust, this idea is called traits. So what we do, we kind of stole this idea have to have a way to manage not only how to specify types, but to say which types get which semantics. So type A supports equality and JSON, whereas type B supports equality and Plutus data encodings. And this is a very useful feature to have in an environment like Cardano, where we are working in a very restricted environment where things like Plutus data encodings can only support a certain set of fundamental types. For instance, we are not working with floating point numbers in Cardano, but that's, for instance, not a problem in any other generic environment that you work with, like the web environment and stuff like that. So Lambda buffers is essentially a toolkit in which you specify your domain types and you specify which semantics those types have, and the whole pipeline essentially generates code that you can use seamlessly. And what LambdaBuffers also provided is Nix-based DevOps tooling, where this process of eh, including dependencies or code generation tooling being invoked in proper order and in proper manner is done for you. So you don't have to do much, but just to specify a Nix build recipe and reload an environment when you change your schema. So this is the main repo, and it contains of all the foundational elements of this project, namely the front-end compiler and cogen. Front-end is basically an implementation of domain-specific language for specifying your Lambda buffer schema. There you specify in a textual format your types and tag them with the semantics that you desire. Compiler takes in form of that schema and checks whether everything lines up and is valid through a process called type checking. Once we have a properly type checked schema and there's no errors to be reported back to the user, um, the final step of the pipeline is invoked, which is called the cogen. And there, the user just needs to specify which cogen module in particular they want to use from the cogen modules that we currently support, namely Haskell, PureScript, Plutus TX, and Plutarch. Yeah, so additionally, we had to build runtimes. So every time that you want to work with your Lambda buffers types and their semantics, you need to also include the Lambda buffers provided runtime libraries for your language ecosystem, which contains certain functions and implementation necessary for the Lambda buffers toolkit to operate properly. And one of the most difficult parts and the most crucial parts of this whole project was to have a comprehensive test suite that will make sure that the semantics between different languages are compatible. So if I perform an equality check in Haskell, the same on a value of a Lambda buffers type, uh, the same check needs to result in the same result in PureScript, in Rust, in any of the supported, of the supported languages. For anybody interested in the repo, we have a very comprehensive documentation maintained in our GitHub pages that you can visit and read through the chapters where we talk about topics of design and internal APIs if somebody wants to contribute or find novel ways of using Lambda buffers. But we also have guides for particular language backends that can help users onboard Lambda buffers into their projects and get them started quickly.